Hello folks, this is Physics 38 and I want to make a little correction here to the syllabus. Okay, and we go Physics 38, right? Let's take a look at modification to the update to the schedule. Okay, so Maxwell's equations electromagnetic waves is going to be, let's see, the correction that I'm doing. Yeah, Maxwell's equation is going to be, and the electromagnetic wave is going to be the last topic that we're gonna cover, okay? And for our third partial exam, which starts on 15th of May 23 at 7 a.m., okay? We're going to have only chapters 28 and 29. Originally we had chapters 30 here. Okay, magnetic field and magnetic field due to current. And not to give you the break, don't forget that the exam is next week. Third partial exam is next week, okay? And I'm gonna finish on the chapter on magnetic fields. So we're a little bit behind here, okay? And there is a what we're going to do today is going to be on Ampere's law, okay? So let's go back here to our video on the Ampere's law. So far, we have seen the following laws of electricity and magnetism. That was the first law we have seen. We have seen E dot dA equal to Q enclosed, right? And that's the Gauss's law of electricity. And there is also a corresponding law for the magnetic field. A magnetic field, the Gauss law of magnetism. But instead of having Q enclosed over epsilon naught, you have a zero here on the other side. I want you to remember that. There's not many problems related to that, but it just what this law states is that there is no magnetic monopoles. There's no sources and sinks for the magnetic field. That's what this law means, unlike the electric field, okay? And what I want to cover now, finish covering today, is another way of solving for the magnetic field using Ampere's law. Here is how we formulate Ampere's law. It's going to be not a closed area integral, but it's going to be a closed loop integral. This ds here stands for loop, okay? And that's an important difference between the electric and magnetic fields. Okay, so every time you see an integral with a closed area like the one above, like the two above, right? The two above. It means that you have a source or sink, either a source, you have either a source or a sink for the field. It means that the field either radiates away or radiates towards the source, which in the case of the electric field is going to be the charge. If you have a zero on the other side, every time you see an integral with a closed area like the two above, right? It means that you have not like the two above, but like the first one above, it means that you have either a source or a sink for the field. It means that the field either radiates away or radiates towards the source. Radiates or points, right? Either radiates or point away or radiates towards the source. If you have a zero on the right side, it means that the field does not do any of that. That's how you should interpret those integrals. Second integral. When you have a closed path integral, like the third one above, it means that the field circulates around the source on the right side, which in this case is the current enclosed by the closed path or loop. Okay, that's what you have to know about that. So we're going to, can you remember that? You know, flux, electric flux, either radiates away from the charge or radiates towards the charge. If we have a zero here, there is no field radiating away or towards the charge. Okay? However, when you have a path integral, closed path integral, what does it mean? It means that the field circulates around the source, which is in this case is the current. Is the current. Okay? So let's concentrate on this integral. Let's concentrate on this integral and let me give you some illustrations, okay? Suppose that you have a bunch of current coming out and into the board, okay? This current is a very long wire that's coming towards you. This other current is another current that's coming towards you, and this is a current that's going into the board. And I go ahead and, you know, choose an arbitrary loop, an arbitrary path, just like this loop number 1 right in here. Okay? The current enclosed by this loop is not enclosed any current whatsoever. Consequently, the current enclosed by this loop is going to be 0. Okay? We can write that like that. I enclosed in this case is going to be equal to 0. That's the geometrical interpretation for that integral. And that's what you need to know to start solving problems. Using Faraday's law. Okay? Now suppose I choose a different loop in which I go around all the three, which encloses all the three currents. Not only enclose all the three currents, but the loop goes in the counterclockwise direction. Okay? So now my enclosed loop is going to be different. Okay? My enclosed loop is going to be, I'm going to emphasize here. Is going to be I1, I'm going to emphasize here, plus I1, okay? plus I2. Why is that plus? There's a reason why it's plus. And let's see, I'm gonna put the last one. The last one is not gonna be plus, it's gonna be minus. Okay. The signs that you see right in here has to do with the right hand rule. Since I choose a loop that rotates in a counterclockwise direction, only those two currents that obey the right hand rule is going to have a positive sign, whereas this other one that's pointing to the board should have, in order to make it to be positive, it had to have a clockwise direction loop. Okay? But since it's not clockwise, it's counterclockwise, we have to include this negative sign. Now let's take a look at this other one, the next one. Here you go. I inverted the direction of the loop. Because I inverted the direction of the loop, now the enclosed current that shows up in Faraday's law is going to be something like that. This guy points towards, points into the board, and consequently its circulation is going to be positive whenever the path direction is clockwise. Okay? And here, okay, here we're gonna have a different loop, okay, that excludes the current I3. In this case, again, is going to be in a direction contrary to the other current. That's the loop number 4, clockwise direction. So you have to have, and it's excluding the current I3, right? And so on. Okay, and so on. That's how you determine the enclosed current. That's the first step that you have to know in order to proceed with with Faraday's law. So now, using Faraday's law, we can start determining the fields in a much simpler way, but only for current distributions that have symmetry, just like for the electric field in Gauss's law. Okay, so we can write it down here like that. We can determine the B field using Faraday's law. Can determine the B field of a symmetric current distribution. Okay? Current distribution. In the same way, we use the Gauss's law of electricity to determine the electric field. Okay? So we are going to come up with one example, something that we already did, that we already solved using Biot-Savart law. Determine the magnetic field of infinitely long straight wire carrying a uniform current. I. Okay? Find the B field at any distance from this wire using Ampere's law. First step is to write Ampere's law. Okay? First step, I'm going to put that in bold-faced and italics. The second step is to identify an Amperian loop by the same token that we identified that Gaussian surface, right, in the past, that is symmetric, not the, that is symmetric with respect to the current carrying wire, okay? So I'm gonna illustrate that here in my PowerPoint slide. This one here, here you go. Here we have a current carrying wire, right? There's no other wires nearby to interfere with the magnetic field. This guy is isolated in space. And how do we solve? We already know how to solve something like that using Biot-Savart law, right? But there is a simpler way of solving the same current distribution using Faraday's law, the integral law. Okay, so we have to choose this a circular Amperian loop that is symmetric with respect to this current distribution. Okay? Okay, so here it wouldn't work if you have chosen an Amperian loop in this way. A circular Amperian loop off center of the current carrying wire. This is, this loop here that wouldn't help you solve this problem. Okay? Because it's not symmetric. Going back to what we had before, right? This one here. And I'm going to copy and paste this one right in here. So the first thing that you have to recognize is that because the current is the source of the magnetic field, if you have some loop, some circular loop like that off center, what does it mean? Why it's not symmetric? It means that this distance here, because this distance from here to here is different than this distance from here to here. It means that the magnetic field at this point, which is going to be stronger than the magnetic field at this point. Okay? So the challenge here is to find a loop that will help you, will make your calculations easier to determine the magnetic field. In this specific case, the distance from the current, which is the source of magnetic field to this point, is the same as the distance from here to this other point, and throughout the whole path. For this reason, it's reasonable to recognize, to assume that the magnetic field intensity is going to be the same along all this path, considering this current alone. Okay? So that's the key. And like I mentioned before, the magnetic field circulates around the current. And then the second step would be to choose the path, right? Let me put a second illustration here to choose. I'm going to choose a path that is counterclockwise, right? A path at a distance r, closed path at a distance r, and which is also counterclockwise, because using the right-hand rule, the thumb will point in the direction of the current. In the next step that you already saw, we have here these magnetic fields circulating around the source. Okay? So remember, and because the distance from the current here is going to be the same, the magnitude of the B1 field is going to be the same as the magnitude of the B2, same as the B3, same as the B4. Okay? So keep that in mind. So here are the steps, right? The Amperian loop is centered at the wire and enclose the current I. Consequently, the right side of the law becomes something like that. B dot ds is equal to mu dot I. Amperian loop. We set the direction of the loop. In that case, I set it counterclockwise. because it is the positive direction for the current that, according to the right hand rule, right? According to the right hand rule, for the current that is pointing away from the plane of the figure, because the direction of the B field coincides with the direction of the loop, okay? We can state that this dot product is going to be just magnitude of B, magnitude of ds, okay? And the enclosed current is going to be I. And now that we know that the magnitude of magnetic field in that Amperian loop is constant, is the same, we can take it out of the path integral. That's what this step is all about. And we are left with calculating the length of the entire path of the loop, which is 2 pi r, right? This entire loop here is going to be 2 pi r. We still have mu naught I on the right side. And when we solve that for the magnetic field, we have this relation mu naught I over 2 pi r, which is exactly what we saw in the Biot-Savart law. Okay? Don't forget that the B field still have a direction, right? So if you're going to write that in terms of a direction, you can write that down in terms of the polar coordinate system, okay? Because B is counterclockwise and theta hat is also counterclockwise, we can just write that down in terms of the positive, right? Now another example. Here you go. We're going to do another example here. Example 2, right? Wire with a finite cross section which has a radius r. Let's take a look here, the next one. Here you go. We have this wire carrying a current. It has a finite radius r. And the current is uniformly distributed in this cross section. Okay, right here. Uniformly distributed in this cross section. We apply the same procedure. We choose an Amperian loop, and I'm going to make a view from the top, right? Take a view from the top without this guy here. So we current rod carrying a current uniformly distributed through this cross section. There's a little trick here that makes things much easier. Let infinitely long and straight rod of radius r carrying a net current I that is uniformly distributed throughout the cross section of the rod. Find the B field at any distance from the center of this rod using Ampere's law. So going back to the drawing, here's my rod that's carrying a current. Here's a cross section of the rod. Current is going towards you. You can even come up. I'm gonna get. Oh. I'm gonna copy this thing here and paste in there to remind you that there is a current coming out of the board here. What do? We go ahead and come up with an Amperian loop inside the rod. Then we're going to do outside. Okay, and we're going to set also the direction of the loop. Okay, which is going to coincide with the direction of the B field. We can state that the magnetic field here, those regions are the same because we have a uniform current distribution. We don't have a concentration of current here and here, right? We don't have concentrations at different spots. It's actually uniformly distributed throughout the whole cross section. And so the first step, write Ampere's law. Okay? But now the I enclosed is going to be something different, slightly different. Second step, identify an Amperian loop that's symmetric with respect to the current distribution. In this case, it's going to be a circle centered at the wire. Okay, and with radius r less than big R. This loop is enclosing a fraction of the total amount of current. Okay, and that's what's going to be the trick for solving this problem. Here you go. This loop here is enclosed. We're not enclosed the whole cross section of the wire. We're enclosed only a fraction of the cross section. Consequently, the amount of current inside this loop is going to be less than I. And there is a way to find out what's this value in terms of R. Okay? So I'm going to copy this R right here and paste it there. All right, there you go. And that's what they're going to do. And then how the key question here, how much of I is enclosed by this loop, right? That's the key question. Let's take a look. Okay, we start here with B dot ds. Oh, that's the trick that we have to do. We have to define something called the current density. Okay, the current density J. Okay, because this J is uniform throughout the whole cross section, this J is going to be equal to the total current I divided by the area, the cross-sectional area of the wire, pi r squared. Okay, and now, we can solve for the I. Okay, here you go. Solve for the I. Here, looks this term is constant, and I'm gonna even write that down instead of I. I'm just gonna say enclosed. This one is not enclosed because of the total current. di enclosed. Okay. We solve this integral. This is a constant, so you can be taking out of the integral. Don't forget it's an area integral. The area enclosed by the loop is pi r squared. Pi cancel out this pi, and then we found out that I enclosed is this value right in here. So that's my enclosed current that I'm going to replace right in here. Okay. are enclosed. That's the one. And now we do exactly what we did before. We recognize that this dot product is going to be magnitude of B, magnitude of ds, because both vectors, they point in the same direction. And they are parallel to each other. Because they are parallel to each other, we can write like that, right? BDS. Because the magnitude of B is the same everywhere along that specific loop, we can take this B out of the integral, and that's what you have right here. And this path, again, is going to be 2 pi r, just like we had before. 2 pi r here. Solve for B. And we get this relationship here for the magnetic field. So inside that loop, inside the cross section of the wire, the magnetic field increases linearly with R. If we repeat that for a loop for the region outside the wire, now it's going to enclose the whole current, and you get the same result as you got for the infinitely long wire. Okay, so you can write that down here. This is for R. This is for R less than big R. For R greater than big R, we get a B field that is the same for a infinitely long wire. Infinitely long wire. Recall that we got something similar for the electric field, right? In a sphere, uniformly distribution of a sphere, the electric field is linearly proportional, directly proportional to the distance from the center. So what we're going to do next, we're going to do that, we're going to apply Faraday's law for the solenoid. Okay, so let's do that for the solenoid. That's another important device that you need to know how the magnetic field behaves. Okay, knowing the current, find the B field inside and outside a very long solenoid of lengths L and N turns. Okay, I'm going to illustrate the solenoid. Here's an illustration of the solenoid. It's a tube in which you wrap around multiple turns of wires, and these wires connect to a battery that's carrying a current along this solenoid, right? Each of those wires is generating a magnetic field, each of them. Let's go back here. Very important to keep in mind, you know. In order to solve this problem, we need a combination of qualitative and quantitative analysis. Okay? So in the first step, we determine, again, notice that is qualitative to solve this problem, right? To solve this problem, we need a combination of qualitative and quantitative analysis. The first step, we determine qualitatively what's the B field distribution at the top of the solenoid. and then at the bottom. Okay? And I'm going to walk you through this qualitative. So here you go. How they do that? We're going to, here's the direction of the current, right? We're going to find out what's going to be the magnetic field here at the top of the solenoid. And I'm going to illustrate the current flowing at the top like that. So that's how you should illustrate your solenoid. Currents coming out of the board at the top and going into the board or the screen, right, at the bottom. If you do that, you will be able to find out what's going to be the magnetic field. But you'll find out only in a qualitative fashion what's going to be the magnetic field. Okay? And I want you to memorize those steps. So here you go. So here you go. We have this wire, one of the wires there of the solenoid, right? Let's say this one right here. We already know that the magnetic field circulates around it. See how important it is to know the behavior of the magnetic field in a wire, around the wire, right? So now we have this other wire next to the first one, which also has a magnetic field that's circulating around it. Notice that this field of this wire is going to cancel out this other field of this other wire. They're not pointing in the same direction, right? So, because they carry the same current and the distance are almost the same, we can say that's approximately, it cancels out approximately. Then we have the third wire. Something similar happens, right? And so on, the fourth wire. So from this simple qualitative analysis, we found out that we have just a horizontal field at the top pointing to the left and horizontal field at the bottom pointing to the right. If you have a bunch of those wires very close together to each other, there will be no component of the magnetic field in the vertical direction. There will be only a component of magnetic field in the vertical direction at the very left region of the solenoid, but that will be negligible. Okay? We do the same for the wires at the bottom. It circulates in the clockwise direction, and we recognize that the fields cancel out here in the vertical direction, right? It's not much different. The field is going to be in the horizontal to the right at the top and horizontal to the left at the bottom. And now we have this configuration that you see here. That's how the magnetic field behaves. I'm neglecting the vertical component of the field here at this spot and at this spot because you have a bunch of wires here. And whatever you have here at the end is going to be just 2 wires out of hundreds of them. So we can come up with this approximation that there is no vertical component of the magnetic field either here or there. Okay? So that's the first step. Let's go look at our from the qualitative. We determined that there are no B fields. There is no B field in between the wires that are wrapped around the solenoid. In the second step, we are going to determine the value of the magnetic field in the lower portion of the solenoid due to the current distribution at the upper lower portion of the solenoid. Okay, so that's when it becomes a more quantitative treatment. Okay, let's take a look at here you go. Notice that the magnetic field generated by this wire distribution is to the right, and this one here too is to the right. Notice that they point in the same direction, right? So because the radius of the solenoid is very small compared to its length, okay, it's very reasonable to assume that the magnitude of the B field due to those wires doesn't change in this vertical direction. Okay? It's very reasonable. But don't forget, not only we are going to have these vectors pointing to the right inside the solenoid, we are going also to have this vector pointing to the right outside the solenoid. And guess what? Even though this field from the bottom reinforces the field from the top, it cancels the field at the top. Okay? That's an important result that we got. B outside the solenoid is going to be approximately 0. Okay? So, here you go. Regions inside the solenoid will be filled due to the current distribution of the lower portion. Reinforce the B field due to the current distribution of the upper portion of the solenoid. Okay, here I'm gonna put in the region outside the solenoid, the B field of the upper portion cancels the B field of the lower portion. Conclusion, B field outside solenoid is negligible, whereas inside the B field is non-zero. So in this, the above we use the fact that the variation of the B field is negligible compared to the field inside, because the diameter of the solenoid is much smaller than its length. So here you go. Here's our first conclusion. It's not the end of the problem yet. B outside is going to be approximately 0. It's going to be approximately 0. Okay, region inside the solenoid, the B field due to the current distribution at the lower portion of the solenoid, and for the B field current distribution at the upper portion, and vice versa, right? And vice versa. In the region outside the solenoid, B field at the upper portion cancel the B field at due to the lower portion. Conclusion, B field outside solenoid is negligible. But we still do not know what's the value of the B field inside. Now we are going to find out what's going to be the B field on the inside using Ampere's law. Let's take a look. Here you go. How do we do that? Here you go. The B field due to the reinforce the upper portion, but also reinforce the lower portion, but also cancels out the B field outside, and that's what we get so far. So far, that's just a qualitative treatment. That's very powerful, by the way. Don't underestimate this type of treatment. What we're going to do now is to find out the value of this B field inside the solenoid. Okay, so here you go. When you superimpose those two fields, you get a longer vector, right? B out is approximately 0. And now we go calculate what's the actual value of this B field inside the wire, okay? I have chosen a symmetric loop, Amperian loop. I've chosen a symmetric Amperian loop, which is denoted by this square. We're going to have leg 1, 2, 3, and 4. Path 1, 2, 3, and 4. Okay, that's what we have here. I have also chosen a clockwise direction, counterclockwise direction. So my B field is going to be positive. Here's the arm 1, 2, 3, and 4. And I give give it a name, an arbitrary length for this wire. Instead of L, I'm going to put A, right? Because L is the length of the solenoid, not the length of the loop. Okay? And then we have to solve this integral here, the path integral over 1, 2, 3, and 4. Let's take a look at the Ampere's law. Okay, here we go. Label the sides of the Amperian loop 1, 2, 3, and 4. Choose the horizontal length of the Amperian loop. I put A, let's put A here, right? A. Apply Ampere's law. B dot dl over the whole loop. We break it down in 4 different paths. Along path number 1, 2, 3, and 4. Okay? And what you end up having here, I'm going to write it down. Don't forget, it's N divided by L is the density of loops. Density of loops. And here, what you're going to have, you're going to have A, not L, not lowercase l, but A. If A is equal to capital L, right, you're going to have NL. And I'm going to write it down in terms of the lowercase n, where n is, lowercase n is big N over L. So let's go one by one. First loop. First loop. Here, the path of the loop is parallel to the magnetic field. Consequently, you're going to have B1 times A. Going back there. Let's going back here. B1, right? Dot ds, they point in the same direction, right? B1 ds, B1 magnitude ds. On the vertical sides of the loop, let's go back here. On the vertical side of the loop, the path is perpendicular to the magnetic field. So B dot ds is going to be 0. That's why I have a 0 there for those, this and this term, right? And B3, B3 is what? B3 is the region outside the solenoid. So 0 times something that's not 0 is going to be 0 as well. So we have this, you're going to put A, right? It's going to be A as well. A is an arbitrary length. And look what we get. Look what we get. I'm just repeating what I have upstairs. Mu naught n AI. This A here, that's arbitrary, is going to cancel out with this other A here. And we end up with this B1. Notice that there is no dependence of B with the vertical length of the Amperian loop. This means that the B field must be uniform inside the solenoids. So the solenoid is the magnetic counterpart of the electric parallel plate capacitor. Okay? Both of them have a uniform field inside and a zero field outside. So that's for the solenoid. Remember that. And this n is, lowercase n is the total length of turns divided by the length of the solenoid. So we are going to conclude this chapter with the toroid, okay? The toroid is nothing but a donut. So here you go, let's just summarize what we did so far. We did so far use Ampere's law to find the fields of the following current distributions. 1. Infinitely long wire, of zero cross section. Infinitely long wire of finite cross section. So, infinitely long solenoid, right? Solenoid. You can put that this way. And then the last one you're going to do is going to be the toroid. So those are the 4. There's a toroid of inner radius A and outer radius B with a wire wrapped around its surface. Given a uniform current I, and that there are n turns of wire wrapped around it, find the B field inside and outside it. Okay? I'm going to illustrate this toroid. That's how it looks like. It's a donut, and we wrap wires around here. We have devices that are sold out there, either in toroid shape and solenoid shape. Okay? And again, we are going to use Faraday's Ampere's law. Okay? Ampere's loop law. How are we going to do that? We are going to visualize those currents going into and out of the board. Okay? In the next step, we are going to come up with my Amperian loop that has a symmetry just like that. Since there is no current pinching this Amperian loop, enclosed by this Amperian loop, the magnitude of magnetic field here inside is going to be 0. Okay? So that's the easy part. Okay, use a circular Amperian loop that's centered at the center of the toroid. We apply Ampere's law for R less than A. Since the enclosed, right? Since the enclosed current is 0, the B field in this region is also 0. And the same thing happens for a region outside the toroid. Okay, here we go. Positive current, negative current, same magnitude because we have uniform current here on both sides. Net current, net or enclosed current is going to be 0 as well. So in the region inside and outside the toroid, the magnetic field is 0. Okay, also 0 is 0. Now the difficult part now is to do solve the magnetic field in that region in between, right in here. Okay, so here we go. This Amperian loop of generic radius r is enclosing all the current, right? So mu naught I enclosed becomes mu naught Ni. Okay, so here you go, mu naught Ni right in here. What else can we state, right? Let's not forget that if you apply right-hand rule, right, the magnetic field due to this current distribution is going to be in this tangential direction, right? In this tangential direction. And the magnetic field of this other one is also going to be in the tangential direction and going to reinforce this one. Just do the right-hand rule. Thumb pointing the direction of the current for the outside current, right, distribution. Right hand tells you the direction of the magnetic field. Magnetic field due to this current distribution is going to be tangential in the clockwise direction. You do the same for the other one, you still get tangential in the clockwise direction. So the B, the distance from the sources is going to be the same because the path is tangential to and the clockwise direction, and we have this dot product. Okay, the B field along that Amperian loop is going to be uniform only along that Amperian loop, and that's what this integral is telling you. You want to calculate only the B along that specific Amperian loop. You can take it out, and then what you have, we have an integral of ds becomes 2 pi r. I encloses Ni. B 2 pi r, solve for B, and look what we get. Something similar than what we got for the wire, right? So that's what we have for today, and that's the material that's going to show up in the exam next week. Okay? See you soon, and see you at the exam. Bye-bye.